Thanks for the help. Hi everyone, my name is Yimeng and I'm a third-year PhD student at Queen Mary University of London. Today I'm going to talk about my recent work on domain-adaptive out-of-context news detection. So, what is out-of-context news? Let's take a look at a couple of real-world examples. So here in this example, the claim says, photos show US senators sleeping in the chamber. But guess where this photo was taken? These are images of members of House of Lords in the United Kingdom. So clearly the image and the claim are not coming from the same event. There is a mismatching. So this piece of news is considered as the out-of-context news. And let's take a look at another example. So here in this example, the claim says, photo shows Tampa Mayor Jane Castor maskless at Super Bowl. And in fact, this photo was taken at Raymond James Stadium on September 30th after the Tampa Bay Lightning won the Stanley Cup, which I guess is from another sports event. So out-of-context news is a popular type of misinformation where a false claim is attached with a real image outside of its original context. And this way of producing misinformation has a very low technical threshold because anyone can trivially attach a fabricated claim to a real image outside of its original context and then post it online. So therefore, we can see it very often in online media websites. Disseminating misinformation is harmful, so it's important to develop some models that can detect such out-of-context news and stop its dissemination. And we further ask ourselves, what if a new out-of-context news domain emerges with no labels yet? Can our model adapt to it well? And this is the motivation of this work. And since there is a wide array of news topics and agencies out there, so here in this work, we focus on the domain as news topics and news agencies. So for the news topic, if we have the labeled data on, for example, climate change and military-related news, and we have unlabeled data on COVID-19 news, can we develop a model that has promising performance on the unlabeled COVID-19 news as well? And for the news agency, if we have the labeled data on the BBC News, The Guardian, the USA Today, can our model adapt to the unlabeled Washington Post news well? So enabling the domain adaptive capabilities of the detection model on both news topics and news agencies will save the annotation costs of those online content moderators. Since the model developed for one platform or for one topic can be extended to some emerging unlabeled news topic or agencies. And therefore, it relieves the operational burden of those content moderators. And then we did a little bit of research on the existing data sets on out-of-context news. And it turns out that there are two available data sets collected for out-of-context news detection. And the first one is Twitter comms. It is collected from Twitter on 3 news topics, namely the climate change, the military vehicles, and the COVID-19. And the other data set is news clippings. It is collected from 4 news agencies, namely The Guardian, the USA Today, the Washington Post, and the BBC News. So here is a formal definition of our problem. In domain-adaptive out-of-context news detection, here we are given the labeled source domain data, for example, the climate change and military vehicles here, and the unlabeled target domain data, for example, the COVID-19 news. And each news is labeled as either out of context or original. So basically, it's a binary classification problem. And our model is trained, during the training time, our model is trained on those given data inputs And during the test time, the model parameters are frozen, and it is evaluated on the labeled target domain data. And note that the source domain and the target domain are mutually exclusive. So the domain appearing in the source domain should not appear in the target domain. And so when we try to devise the model to tackle with this problem, there are some ideas that underlies our approach. So the first one is that, so after we encode the out-of-context news into some multimodal representation, our goal is to find a decision boundary that can well separate the news from both labels. However, this is not so easy, because in these data sets, when they construct the out-of-context news, they are constructed in a way that makes them semantically similar to the original news. So this makes those circles and crosses stay close to each other in the representation space. And it could be subtle for the model to identify the differences. So what we want to do is, our intuition is to widen the distances between the circles and the crosses, which separately denote the out-of-context news and the original news. So how we did that, for each news item, we generate an augmentation news item here. And in implementation, we use the Gaussian blur applied to the image-only modality. So this preserves the label because it doesn't change the semantic meaning of the news. And next, we aim to pull closer the anchor news item and its augmentation news item. And at the same time, we hope to push further the news item, the anchor news item, with all the rest of the news item in the same batch. So in this way, we end up learning a sparser representation space so that we can leave more room for the decision boundary to be drawn. And secondly, since we are doing the domain adaptation in out-of-context news, we hope to, our assumption is that if we manage to learn a feature that the probabilistic distribution of this certain feature are similar or the same between both the source domain and the target domain, then we assume that this certain feature has the domain-specific information removed and the domain-invariant feature kept. So the goal of our model is to make sure that those two figures, the distributions, has smaller discrepancy or has more similarity. And lastly, since we only have the we only have the unlabeled target domain data during training, so this branch of data inputs is not passed to the classifier during training. However, we still want to leverage some target domain knowledge, so we can do it. We hope to do it during the test time because we leverage more target domain knowledge. We expect that it could further boost the model performance. And when we put all of our ideas together, we end up getting this final model architecture. So given the news input from both the source domain and the target domain, firstly we use a multimodal feature encoder to obtain the multimodal representation of this news, and then we aim to learn the domain invariant feature by applying the contrastive laws to learn a sparser representation space, and then we apply the maximum mean discrepancy, MMD in short, to learn the domain invariant feature. And lastly, we pass the learned source domain feature to the classifier and use it to train the model during the training time. And during the test time, we pass the target domain data through the multimodal feature encoder and learn the projection head. And we apply test time adaptation to the classifier so that it could include some of the target domain statistical information and which is conducive for the model performance. And here are some experimental results. So firstly, the x-axis displays the 7 domain adaptation settings in these 2 data sets, because we have 3 news topics, 4 news agencies, so we have 7 domain adaptation settings in total. And then in the implementation, we use the BLIP2 multimodal feature encoder as to encode the news. So first, we want to test its vanilla performances, or the lower bound performance of this feature encoder. So what we do, we use a simple linear classifier following the multimodal feature as the inputs, and then we train the model using the source domain only and test it on the target domain. And the evaluation performance is shown in this blue dashed line. And we also want to see the upper bound performance of this feature encoder. So this time we use both the source domain and the target domain data during the training, and we again test the model on the target domain. So both these 2 models are the same simple linear classifier. And so the orange line shows the upper bound performance of this feature encoder. And the area between these 2 lines suggests the domain adaptation gap of these domain adaptation settings. And then we pick out some baseline models from a relevant closed task, domain adaptive fake news detection. And these are the performances of those baseline models. And then we compare our model to the baseline models. So this bold pink line is our model's performance. And as we can see, it outperforms in most of the domain adaptation settings. And then we want to check out if the domain invariant feature is actually learned by our model. So this figure shows the BLIP2 multimodal feature the BLIP2 multimodal feature we get from that feature encoder. And so these are the input embeddings of our model. And we can see that the data points tend to stay closer with the other data points within the same domain. So here the red points are clustered, and the blue and gray points are somewhat clustered. So this is the input embedding, how it looked like. And in the right figure, this is the learned domain invariant feature by our model. And we again apply the t-SNE visualization. And this time we can see that the data points are more scattered, especially the red points. So this suggests that the spatial distribution of those data points are not conditioned on the specific domain anymore to some extent. So we assume that, we think that the domain-specific information is removed to some extent, and the domain invariant feature is learned. And in conclusion, we are the first to investigate the domain adaptation in out-of-context news detection, and our approach achieves total performances under most of the domain adaptation settings. And in our future work, we hope to be able to evaluate the model on a wider array of real-world news topics or agencies. Thank you so much for listening. Here's some of my personal link. Thanks. That's it.